All right, welcome. Ever wonder what makes our world work? From the incredible bridges you drive across every day to the smartphone that's probably in your hand right now, there's a certain way of thinking behind it all.
So, what is the secret sauce? Is it just a ton of complicated math and physics? Well, not exactly. It's really a powerful way of thinking, a specific mindset for tackling real world problems. So, let's get into it.
Okay, so we're going to break this whole engineering mindset down into 5 core ideas. Think of these as the building blocks that drive, well, pretty much all of modern engineering. And the cool thing is, you can use this framework for almost anything. All right, idea number 1. It's all about learning from both success and failure. Now, it's easy to focus on the amazing wins, right? The incredible triumphs. But engineering as a discipline, it's really built on the tough lessons learned from some pretty catastrophic failures. Both sides of that coin are absolutely critical. I mean, look at the successes. They show us what's actually possible. Aviation, for example, it completely shrunk our planet. A trip that took weeks now takes hours. And your smartphone? Come on, that's a literal supercomputer in your pocket that's changed everything about how we live. These wins push the boundaries. But what happens when things go wrong? And this right here, this quote gets to the heart of it. In engineering, failure isn't the end. Not at all. It's just data. It's a strict teacher for sure, but it's the feedback you absolutely need to build something better and safer next time. And speaking of strict teachers, there's maybe no better example than the Tacoma Narrows Bridge collapse back in 1940. I mean, can you imagine? It started with some high winds, then the bridge began to sway a little, and then it started twisting violently. Just a few hours later, the whole main span just ripped itself apart and plunged into the water below. Now, thankfully, everyone got off in time, but that image, that failure, it became a defining lesson for generations of engineers to come. So what happened? The culprit was this wild phenomenon called aeroelastic flutter. Now, they didn't fully get it back then, but basically the wind and the super flexible bridge deck got locked into this dangerous dance. The wind would push the bridge would move, and that movement would change the airflow in a way that pushed the bridge even harder. It was a self-reinforcing vibration that just grew and grew until the structure couldn't take it anymore. So this leads us straight into our second big idea, and it's a huge one. Great engineering doesn't just pop out of someone's head in a single eureka moment. Nope. It's forged in a relentless cycle of improvement. It's an iterative process where failure isn't just something to be avoided. It's actually part of the plan. And this is that cycle. It's the core loop of engineering. Build, measure, learn. It's so simple but so powerful. You build a version of your idea, a prototype. Then you measure its performance. You test it, you push it, you see where it breaks. And then you take all that data and you learn from it. That learning feeds directly into the next and hopefully much better version. Right. And you don't just jump to building the final expensive thing. Smart engineers start with what we call low-fidelity prototypes. These are cheap, they're fast. Think cardboard models, rough sketches, maybe a foam mock-up. The goal is just to test the basic idea and try lots of different things without breaking the bank. Then, once they've got a concept that works, they move on to the high-fidelity prototypes. These are the fancy ones, made from near-final materials, ready for some serious, detailed performance testing. Okay, let's keep going, because this all connects. This brings us to idea number 3, the art of the trade-off. You know, in the real world, there's almost never a single perfect solution. Every single engineering decision is a balancing act. It really is a constant juggling act. You want to make it stronger? Okay, but that's probably going to make it heavier and more expensive. Want it to look really sleek and beautiful? That's great, but it might make it a nightmare to repair. You're always weighing these competing demands: cost, performance, safety, reliability, even how it looks and feels. This decision matrix is a perfect example of how engineers think through these trade-offs. Look at the options for a bridge. A simple beam bridge, super cheap, easy to maintain. But it can't span very far, and let's be honest, it's not going to win any beauty contests. On the other end, you've got a suspension bridge. It's an icon. It can span for miles, but the cost and complexity? Through the roof. So the best choice isn't about finding perfection. It's about finding the optimal compromise for that specific problem. All right, we're on to our last 2 ideas, and they really go hand in hand. This is all about how engineers tackle the messy, unpredictable real world. They do it with 2 super powerful tools. First, they simplify reality by creating a model, and second, they build systems that can react and control things all on their own. Just think about something like traffic. It's chaos, right? Thousands of cars, thousands of drivers, all doing their own thing. You could never calculate all of that. So what does an engineer do? They simplify it. They create a model. Instead of tracking every single car, they might treat all that traffic like it's water flowing through a pipe. Now, is it a perfect representation of reality? Of course not. But it's simple enough to analyze and good enough to give you really useful insights. But the real magic, the really clever part, is what's called closed loop or feedback control. This is where a system gets a kind of intelligence. It's designed to constantly measure its own output, compare that measurement to the goal you gave it, and then, here's the key, automatically adjust itself to correct any errors. Your car's cruise control is the perfect example of this in action. You set the goal, the set point, let's say 80 kilometers per hour. Then you start going up a hill. A sensor measures your actual speed and sees, hey, we've slowed down to 75. The controller inside calculates that error, we're 5 kilometers per hour too slow, and it sends a signal to the engine to give it more gas. It's this constant automatic loop. Measure, compare, correct. Measure, compare, correct. All without you doing a thing. Okay, so let's wrap this all up. Let's recap the 5 pillars that make up this incredible problem-solving mindset. So, number 1, learn from everything, the good and the bad, success and failure. Number 2, always be improving with that iterative cycle. Build, measure, learn. 3, become a master of the trade-off because there's no such thing as a perfect solution. 4, simplify the messy real world with models so you can actually understand it. And finally, number 5, use feedback loops to create smart, self-correcting systems that achieve their goals. And here's the thing. These 5 ideas, they're not just for engineers building skyscrapers or coding software. This is a framework, a way of thinking that you can apply to pretty much any challenge, big or small. That, right there, is the heart of thinking like an engineer. Thanks so much for joining this explainer.